Okay, good morning. Welcome to
KidMath107.
KidMath number 107. So yesterday we talked about formula for the Fibonacci numbers. They were sort of this process with the functions, right?
Yep.
Fn plus 1 equals Fn plus Fn minus 1. And we looked at starting point of these numbers. Started at 0 and 1, and then we just kept going forward, adding the previous two to get the next one. Okay, makes sense?
Yep.
And we compared it to what?
To a parabola.
A parabola. And it looked like in the beginning, if we looked at 0, so this is 0, 1, 2, 3, 4, fifth term, and sixth term, etc. It looked like the parabola y equals x squared, which would be 0, 1, 4, 9, 16, 25, was quite a bit bigger.
In the beginning.
But it turned out only bigger in the beginning, and as you did more terms, the Fibonacci numbers caught up quick and then went way higher.
Yeah, at term 11 actually.
Yeah, term 11.
They were bigger.
Yeah. So, or maybe it was 12. It depends on how you start numbering. It depends what you call the first term. If you call this the first term or that one. But anyway, that was interesting, and it was amazing how quickly the Fibonacci numbers grew. And it looked like a more relevant comparison was to 2 to the x. So 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 16, 32. Now, it always was smaller than this when the numbers got big, but it looked like it sort of grew the same way.
It got big faster and faster.
Got big faster and faster, and that gave the idea to say, what if this Fibonacci function, Fibonacci of n, was some sort of exponential, a constant times some number of lambda to the n. Okay? And it was just something that simple. So like for example, maybe the Fibonacci, the nth number would be 3 times, I don't know, 2 to the n, or something like that. That's what I mean. Some constant that's the same for everything, like 3 times some number to the nth power.
Yep.
Okay? And that's what we looked at yesterday, but let's review that today for our movie.
Right.
So if that's true, if the Fibonacci, if the nth one is some constant times lambda to the n, what's the n plus first term going to be?
It's actually n plus 1 would be c times lambda to the n plus 1.
C times lambda to the n plus 1 equals, what's the nth term going to be?
C times lambda to the n.
C times lambda to the n. And what's the n minus 1 term going to be?
Plus lambda plus c times lambda to the n minus 1.
Minus 1, okay, there we go. Now, so now we have an interesting equation involving these lambdas. What's the first thing you think we might do with this equation?
Well, we can just divide everything by c.
Okay. What do we have to be careful about, though?
If c is positive, c has to be not 0.
C has to be not 0, but if the constant was 0, that would mean every term would be 0.
So it works, but
that would work for the formula, but it wouldn't be very interesting, right?
That would be a little boring.
Okay, so let's do that. Let's divide through by the c to get rid of it, and we'll figure out what that constant is later.
And then maybe we should move these lambdas to the other side to get all the lambdas on one side.
Okay, lambda to the n plus 1 minus lambda to the n minus lambda to the n minus 1 equals 0. All right, this looks like a polynomial.
Yeah. So
Any guesses how we might want to solve this polynomial?
we could factor out. We could say if we factored out an n plus 1. Actually, factoring it out an n might be simpler.
Okay, let's factor out an n, lambda to the n. What are we left with on the inside?
Lambda to just lambda.
Lambda to the first.
Minus 1.
Minus 1.
Minus lambda to the minus 1.
Minus 1 over lambda, or lambda to the minus 1. Now, that's interesting, but this is still an equation that we don't quite know how to...
And we don't like that fraction.
Don't like that fraction. So let's factor out something a little slightly different than that.
Maybe an n plus 1?
Okay, what would we get if we factored out an n plus 1?
Well, we just get...
Lambda to the n plus 1.
Yeah.
What would we get?
So we'd get 1 minus lambda to the minus 1. Oh, I still got the fraction.
Yeah.
Maybe lambda to the n minus 1.
Ah, lambda to the n minus 1. Okay, now this looks maybe interesting. What do we get when we factor a lambda to the n minus 1 out of this?
We get lambda squared.
Lambda squared
minus lambda, and then minus 1.
Minus 1. And this whole
Awesome.
thing equals 0. Why awesome?
Because we don't get any fractions.
1, we don't get any fractions.
And this looks like a regular quadratic.
It's just a quadratic. So if this equals 0, if this product equals 0, either this is 0, which just means lambda is 0, which again produces a not very interesting sequence.
Yeah. Alright.
Or this is 0.
So maybe
Okay? How do we solve this equation? How do we find when this equation is 0?
well, we can use our quadratic formula.
Okay, which says negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, so fill in the numbers for me.
So it would be 1.
1, negative 1.
Yep. Plus or minus the square root of 1.
Okay.
Actually, plus 4 over 2.
Over 2. And real quick, should we get a calculator? 1 plus 4.
It's 5.
There we go. So look what we got. The possible values of lambda are 1 plus or minus the square root of 5 over 2. Have you ever seen these numbers before?
Not really.
No? Okay. Yeah, though. But that's okay. We'll come back to it. I want to stop this now. We'll pick this up tomorrow. But the amazing thing that we've just found is there is some connection between the Fibonacci numbers and the square root of 5. That certainly wasn't obvious before when we were doing 1, 1, 2, 3, 5, 8, 13, right?
Yeah.
So this is neat. So this is a very interesting way to look at the Fibonacci numbers, and tomorrow for our movie we'll use this to construct a formula for the Fibonacci numbers so that we can actually, if I can just say to you, hey, what's the 100th Fibonacci number, you can just plug it into the formula rather than having to calculate every one up to that
Yeah.
to get it. So it's pretty cool that we can solve that problem.
Yep.
And it's pretty cool that it's related to the square root of 5.
Yeah.
All right. Good job, sweetie. Good job.